All right, our final speaker in the session is Margie Friedrichs, and she's going to talk about oxygen in the Chesapeake. Take it away.
Great. Okay, thank you very much, and thanks again thanks Ben and the organizers for putting this great session together this morning. I guess this is working. Can you hear me? So today, I'm going to talk about some long-term changes in coastal oxygen. And how changes that we've seen over the past several decades and changes that we may, and actually the past century, and changes that we may see over the next century as well. And in coastal systems, understanding the various different mechanisms causing these long-term changes is difficult. These coastal systems are very complex because we have the global anthropogenic stressors as well as a multitude of local anthropogenic stressors as well. So we've got atmospheric temperature change, we've got sea level rise, we've got precipitation pattern changes, changes in ocean circulation. All of these impact the coastal oxygen budget. And on top of that, we've got urbanization, we've got land use change, increases in fertilizer, wastewater treatment plants. So all of these things are impacting coastal oxygen concentrations. And this is a really interesting, there are tons of interesting scientific questions here and also a lot of interesting management questions. So the managers are very heavily involved in this as well. So before I go any farther, I just want to acknowledge some of my collaborators. First, Pierre St. Laurent at VIMS, and I'm going to show some of his preliminary work today. And my former student, Ike Irby, I'm going to show some of his results from his dissertation work. I want to thank my current students and my collaborators at Penn State, ODU, Auburn University, and the University of Maryland as well. And also want to thank the managers at the Chesapeake Bay program and the scientists there. These are EPA, NOAA, and USGS folks. They've really helped motivate this work, and they've really helped make sure our research is really relevant to the managers. And I like to think that our work is hopefully helping them address some management questions as well. We run often similar models as the ones that they run, and when our results show the same results as theirs does, this leads credence to what they're finding, gives their management decisions they're more robust and people believe them. And then also, when our results contradict theirs, we've got that happens too, and I'm going to show some cases of both today. So you can learn a lot from that as well. So this working with the managers is really something that's really been an important aspect of our work over the past several years or decade, and that's going to kind of be a theme of the talk as we go through today. So over the past century, of course, we've heard a lot today about how hypoxia is increasing, oxygen concentrations are going down. So here's a figure from Carstensen et al. Showing how this is occurring in the Baltic Sea, how we're getting more and more hypoxia. The red zone here is hypoxia, black is anoxia. So over the past century, from 1906 to 3155 up until 2012, you can really see this increased area of hypoxia. So this is not only happening in the Baltic Sea, of course, but in coastal regions all over the globe. In particular here, I'm going to be focusing on the Chesapeake Bay here on the North Atlantic East Coast. And so here are some results from some of our modeling work where we've tried to estimate what bottom oxygen concentrations would look like in 1903 in the summer. And here on the right, what they would look like in 2003. So you can see this is using some results from the dynamic land ecosystem model, providing nutrients into the estuary. And so you can really see what the difference in bottom oxygen concentrations in the 100 years ago compared to today, where the main stem is really just filled with hypoxic water in mid-July. So why is this happening? Well, it's primarily local anthropogenic changes. So in this figure here, we have inorganic nitrogen loading from this dynamic land ecosystem models from our colleagues at Auburn University. It's a time series of inorganic nitrogen loading to the bay from 1895 to 2015. And you can see over the first half of the century, you can see a gradual increase in nitrogen loading. And then in the 1960s, after World War II, you can see this just spiked up. And it happened here in the Chesapeake Bay watershed and in watersheds all over the country and globally as well. After that, they remained high. You can begin to see a little decrease here, maybe, so hopefully some of these management actions are taking effect. But on top of that, all of those, the local anthropogenic changes, again, we've got these global anthropogenic changes as well, right? So we've got increases in atmospheric temperature here. You'll see the red zone right over, you can't see it very well probably, but that's right over the US. So we've got a large increase in atmospheric temperature. And of course, we have global sea level rise impacting everywhere as well. So if we zoom into the Chesapeake Bay region, here I have a figure showing the increase in annual average air temperature in Maryland from over the past century, from 1895 to 2015. Simultaneously, we have increases in sea level rise, too. In the sea level rise increases in this Chesapeake Bay region are some of the greatest in the, across the globe. We've got this global sea level rise going on, and on top of that, we have this far field glacier rebound impact, and we've got changes in the shelf circulation, which are all working to increase sea level rise. So that is a dramatic effect in this region as well. So basically one of the questions that we're trying to answer, a number of people are trying to answer in this Chesapeake Bay community, is really over the next century, how are these local and these global anthropogenic impacts going to work together to impact coastal oxygen, given these complex feedbacks that we've seen many of which today, examples of today between the physical, the chemical, and the biological processes involved. So this is a really interesting scientific question, but also it's a really important management question. So the managers are really interested in for instance, better understanding how much more difficult it's going to be for them to meet their oxygen restoration goals when they account for climate change. Those goals and the nutrient reductions to achieve those goals were all set without any climate change in mind. So what happens now that climate change is happening? That's what they're wondering. And also, secondly, how much greater would their progress be if we didn't have climate change? We're making some progress, but maybe it would have been a lot better if we didn't have all this warming temperatures, increased storms, everything else. So these are questions that they're really focused on. So the Bay Program, the Chesapeake Bay Program, is the local regional management agency that's really dealing with the restoration of the Chesapeake Bay. And they use a very sophisticated linked watershed hydrodynamic water quality modeling system. And they've implemented this to try to start to answer some of these questions. And so some of their preliminary results from a couple of years ago showed that, for two things. First, that the impact of climate change was actually much less than the impact of these nutrient reductions that they've set in place. So if all the management actions are done and the nutrients are reduced, that's going to, the impact of climate change is going to be a small change to that. So that was actually relatively good news. Their other result was that actually climate change, they predicted, was going to increase bottom oxygen. And this was mostly going to happen due to sea level rise. So this was a really kind of surprising result, like really? So at the same time, one of my students was at the later stages of his dissertation, and so he just took this question for his final chapter in his dissertation. Basically what he did was to redo these climate change experiments that the managers had done and the Bay Program had done, but used a different model, so an alternate modeling system, forced with identical model outputs to try and see, okay, well, do we see the same thing or not? And the managers were very excited to have us do this because they really wanted to either figure out, well, if they're wrong, better to know early, and if they're right, then if we get the same result, that makes them much more confident in their results as well. So my students, it was Ike Irby, and so this was published recently in Biogeosciences, actually written up in an OCB blurb recently too, so you might have seen it there. Basically, he took the Chesapeake Bay, the official Chesapeake Bay watershed model, all the riverine inputs that are the nutrient that comes off of the land are provided by that model, and we put it into a ROMS simulation, what we call CHES-ROMS ECB, standing for estrogen carbon biogeochemistry. And he conducted 4 different simulations. 2 were with different nutrients, so the first used realistic nutrients from the 1990s, that's the manager's period of interest still, so we have to deal with that. That's another side story. And then reduced nutrients, which we call TMDL, or total maximum daily load. So we've got these 2 different, basically high nutrient, low nutrient conditions for the scenarios, and then also 2 different climates. So he used 1990s climate and a 2050s climate. And for climate, he assumed that there was 3 different effects going on. The water temperature was warming, there was sea level rise, and there was changes in riverine inputs. So, and then with these 2 different nutrients, 2 different climates, he has 4 different simulations. So first he had to choose what to assume about 2050. So of course we could, there's lots of different ways to do this. What he did was look at the literature and try to get some reasonable assumptions, or what other people had thought projected to happen by 2050. So in terms of water temperature, the general feeling is that the water temperature is going to increase by about 1.75 degrees. That's probably a conservative estimate by 2050. Sea level rise is going up by about 0.5 meter, and river discharge is going to change primarily just in winter by about 10%, maybe a little more. So that's actually a relatively small effect. So again, he did these 4 different simulations with the different nutrients and climate change, and that's what I'm going to show you here. So here he's plotted bottom oxygen concentration for these 3 years. So here, of course, this is summer when oxygen is low for 93, 94, 95. So the 4 different curves are the 4 different simulations. If you look at black and gray, these are both the base nutrients. If you look at green and blue, these are both the reduced nutrients. So you can see right away, the first impact here, first thing you can see is that the black and gray are considerably lower oxygen than the blue and green. So again, this is basically reiterating the result that the Bay program found, that the change in nutrient inputs is going to have a much bigger effect than climate change. So that's kind of good news for the managers. Then the next thing that we found was slightly different than, well, in fact, completely opposite from what they found. If you look at the gray and black line now, it's a small effect, but actually the gray line with climate change is making hypoxia worse in the bay. So it's lowering oxygen concentration. So basically, we're finding that, I'm going to take that off, the management efforts are going to have to be greater than we originally thought. So this, again, is completely opposite to what the Bay program managers. So they were like, that's interesting. So we then, of course, we wanted to know why. So the next thing Ike did was to look at the different mechanisms, right? So he assumed 3 different components to climate change: sea level rise, temperature, and precipitation, or rivers. So we did 3 more experiments to kind of tease apart these 3 different effects. And that's what I'm showing here. So he's got the change in bottom oxygen over again now in 93, 94, and 95. The green line is 0. So first of all, the blue line here represents the climate change with all of the different climate change impacts occurring simultaneously. The red line is for just temperature. So we just have the temperature warming. And you can see, hopefully here, that the blue and red line really follow each other. So basically, this is showing that temperature is really having the greatest impact on hypoxia here, on oxygen. Mostly, also he goes on to show that most of it, about 75%, is due to solubility. In the spring, respiration does have a significant impact, but solubility is really the main part of the story. So it turns out that actually the reasons our results were the opposite of the Bay program's results was simply that they had underestimated the coastal ocean warming, which is a really big impact here in the mid-Atlantic. So once they fixed that, then our model results agreed much better. So next, the orange line, this represents the changes in river inputs, basically due to changes in precipitation and evapotranspiration. This had a relatively small impact on oxygen concentration, so it's of less interesting. But the more interesting thing here is the sea level rise. We also, just like they found, show that, how come I dot? Oh, there it is. Well, it's a very small dot. Okay, the purple line there, which I can't point to anymore, shows an increase in oxygen with sea level rise. So again, that's exactly what they found. So why does sea level rise increase bottom oxygen? Well, this is a really interesting question. Ike was actually done with his dissertation and out of here, moving on to policy in DC. So Pierre St. Laurent at VIMS has been taking over this question, looking into this question. And this is working very closely with the managers because they're really interested in why is sea level rise increasing bottom oxygen. So what Pierre, one of the first things Pierre did is work with our colleagues at the University of Maryland, Ming Li and his student Wenfei Mi. And they have a very similar modeling system. So let's see, what does their model say? Does they also agree that sea level rise increases oxygen concentration? Well, it turns out no. They show the opposite result. So here on the left, we have, again, Ike's results showing sea level rise increases bottom oxygen. Here their results are shown in terms of hypoxic volume, but they're also showing that the hypoxia increases. So sea level rise is decreasing oxygen here and increasing here. So now what? So why do we see these opposite results in these two models? So basically, both models do indicate, the first thing that we checked was that both models are showing that sea level rise is increasing estrogen circulation, and yes, that's what is kind of is well known to occur, and that is both models are showing that quite nicely. So why do they have the opposite effects on oxygen? So we had a couple different hypotheses. The first is, well, maybe one model is showing that sea level rise increases oxygen because we get more high oxygen water coming in from the shelf. That was a nice hypothesis. Another hypothesis is that one model shows that sea level rise is decreasing oxygen because it brings in more salinity from the shelf. So when it brings in more salinity, stratifies the water, can't get that high oxygenated water from the surface down. So very nice. I really like these hypotheses, but quickly Pierre showed, nope, they were both wrong. Turns out that the models have the same oxygen and the same salinity advecting in, so that can't explain the difference between the models. So another possibility, well, maybe one model is just wrong. I know, all models are wrong, but maybe one isn't reproducing the observations as well. So he went and did a very careful analysis of the relative skill of the two models. Here I've got plots of, in the top panel, Chess-ROMs, in the bottom panel, ROMs. Oh, dare I take this? And then here, I'm going to show a bunch of these different figures. This is, these are all transects up the main stem of the bay. So the south is on the left, north is on the right. And then the dots, which you can see some places and not others, are the observations, right? So we've got oxygen, salinity, and temperature. So where the dots kind of fade away into the background, that's where the model reproduces the data quite well. And where they stand out, you can see that it doesn't. But anyway, after the long analysis, it turns out both models really reproduce the observations equally well. There's no way to determine whether one model is right and one model is wrong. They're both doing equally well. Okay, so moving forward, what Pierre then did was apply a 1 meter sea level rise experiment to both models. So here we have the results of that. Again, it's back. Chess-ROMs on the top, ROMs on the bottom for May and July, and we're looking at the change in oxygen in response to this 1 meter sea level rise. So you can see here, red is decreasing oxygen, red is bad. We've got decreasing oxygen similarly at the surface in both models. But the difference is at the bottom. We're seeing increases in oxygen in this model and not in that model, although it's a little blue, so we got kind of the same effect here, but it's not nearly as strong. So why is this? Is it the physics? Is it the biology? Is it the chemistry? There's so many different possibilities. Well, the first thing Pierre looked at was kind of the physics and looking at the salinity and temperature. So here we're looking at the change in salinity and the change in temperature due to this 1 meter sea level rise. Essentially, both models are reproducing giving the same result for the change in salinity. But it's the change in temperature here that is very different between the two models. So the same amount of salt is coming in, but somehow this, and cold water is coming in the summer. This is for July, so you're getting cold water from the shelf, but it's hanging around in this model and not in that model. So why is this? Well, this is basically where the story ends. This is how far we've gotten. So, but we do have a few different hypotheses. And essentially, we believe, so what our current thought is that it's really due to different physics, and in particular different vertical mixing schemes. So essentially getting back to how important vertical mixing is, which is one of the messages from Malcolm's talk earlier today. So in Chess-ROMs, we're getting the cold water advected in from the shelf, and that reduces respiration. Oxygen increases in the bay with sea level rise. In the other model, it turns out this higher vertical mixing causes surface heat fluxes to, it has a higher vertical mixing, and as a result, the warm the heat fluxes from the surface end up warming that cold water, so it does it before it reaches the low oxygen, the hypoxia zone, the dead zone farther up in the bay, so it doesn't have an opportunity to have that oxygen increase. And there's a second impact. We think that also there may be differences in the biology as well. The Chesapeake's EZB model has a respiration that seems to be more sensitive to temperature than the one used in the UMC's model. So as a result, the colder water is coming in from the shelf, may be causing a greater decrease in the respiration rate for Chesapeake's than UMC's ones. So just to conclude, a few take-home messages here. Basically, all the models agree that the oxygen response to the planned nutrient reductions are going to be much less than due to climate change. But still, we're kind of getting the feeling now all the models are generally coming to a consensus that restoring the bay is going to be harder than we thought because of the because of climate change, and particularly because of the warming bay. And as I say here, the warming bay waters are really going to decrease the oxygen. Changing river inputs have a minor effect. And sea level, the results are really still unclear, right? It depends on our assumptions on what we say for vertical mixing. It depends on our assumptions that we use for estimating temperature dependence of oxygen consumption. So that's still a bit unknown. So I guess just ultimately take home, this is looking at the impacts of climate change on coastal oxygen concentrations is a really complex problem involving these global and local anthropogenic stressors. Involves physics, chemistry, biology, all of it. I think another really important message is that it's really important to use these multiple models when working with the managers and when working with these complex systems. We could have easily just run one model and said, oh yeah, sea level rise has this impact. But then when we started looking at these different models, we kind of get to understand why some of these things are happening. And finally, it's really possible to really work closely with coastal resource managers and really provide useful input and at the same time do some meaningful and interesting science. And I'll end there.
All right, questions for Margie before we move on to the panel?
Statistic Montgomery College. I was wondering what the bottom topography would influence the sea level rise in terms of what you saw, because the relative influence of bottom topography is going to be reduced when you have sea level rise.
Yeah, it's a very good question, and that was one of the things that we looked at was whether one model had a different bathymetry than the topography than the other, but it turns out they're quite similar. But yes, it does absolutely have an impact. The bathymetry and works together with sea level rise to have an impact on climate. Good question.
Hi, Margie. This is Malcolm Scully. I had a question. In a lot of systems, dredging has a bigger effect on the depth than sea level rise. Has that been looked at in Chesapeake Bay? In the northern part, I know they dredge up near Baltimore. Are the managers interested in that? And have you looked at the effects of dredging?
So I think I would say probably other managers than the managers I'm working with, but those managers should get together. Yeah, it's a very good point. I mean, essentially in the model, right? You can either just dredge out, you can raise the sea level, or decrease the bathymetry. It's the same effect. So I would think that would have a significant effect if it's a large enough area. Yeah.
Hi, I'm Karen Stamieshkin from VIMS. I was curious if the models take into account that if you have sea level rise, a lot of coastal homes will probably not exist anymore, and so a lot of sewer effluent could be decreased in that area. Is that something people are talking about?
That's interesting. I think generally, although yes, it's true, there would be fewer houses on the coast. I think there's still the feeling like there's going to be more people in Washington, D.C., which are going to make up for the people not being along the coast. But yeah, and it's certainly not something that we have in the model, but it's true. It's not only houses that won't be there, but land, so there's a big there's a lot of interest in how in all of these models that I talked about today, when sea level rises, it just goes vertically. It doesn't go horizontally onto the land, and that's another kind of a whole another issue that we're trying to work on that is a big problem. So.
Hi, Margie. Jerry Chiputra. Maybe I missed this. Did you take into account the climate change impact on the boundary inflow of water mass into the Chesapeake Bay? Because in our regions in Norway, this water mass from the Atlantic affected by climate change affect the oxygen concentrations in the fjord system. Just curious.
Yeah, so on the open boundary, whether we're taking into account the oxygen and yes. So we are taking into account, and that actually was one of the reasons our models didn't agree at one point. They didn't warm that outer boundary enough because we're finding that the shelf waters are warming quite a bit, so it is important to take into account.
I have a question.
Yeah.
At the end, you talked about the importance of the relationship between temperature and respiration rate. How well is that constrained in the world?
I don't think
Oxygen
very. Well, the modelers need to know it better. If someone knows, so two modeling groups are having quite different, using quite different assumptions, and it looks like what we really need to know is the relative temperature dependence of production versus respiration. So are they going to go up the same? Is respiration going to increase, I think, with temperature more than production? And it's really that difference between the production and the respiration and those two temperature dependencies that's really important to know. Yeah, I think if we could know that better, that would be.
Anna Nanadesic and Johns Hopkins. So I also just want to give a shout out to Margie for making this model available to other people. She's really great about it and great about making the data available, and that's a real gift to the community, so thank you for that. One of the other differences that you just alluded to are these differences in the structure of the physiology of the phytoplankton between the models, because the Chesapeake Bay model has a very, very different, highly tuned phytoplankton community, and ROM's does not. Do you think that's important?
Yes, I think, from what we've seen here, it's really how the models, it seems to me in terms of this one question that it's how production is going to increase with temperature and how respiration is going to increase with temperature. So, their model has multiple different phytoplanktons. Actually, their diatoms end up decreasing.
Yes, exactly.
with temperature, which they cannot convince
That
them to do otherwise.
That was my point, because their large phytoplankton has a maximum at.
Yeah. So I made part of it go flat. I have suggested that it's going flat now. But yeah, whereas most of the other models assume that as one phytoplankton dies out in the warmer world, another one will take over and like those warmer temperatures. So so it's kind of the temperature dependent, rather than the number of phytoplankton species, it's kind of the temperature dependence of those phytoplankton. And that's so important. Yeah.
Andreas Oschlies, do you account for respiration of the sediments, and might that change with temperature, warming of the sediments, so you might have lots of organic material, or the legacy of previously buried material, which might be available again for respiration?
I would say that the various models do that in varying extents, probably not as well as should be, but I think that's really important.
Okay, let's thank all the speakers again. And ask all the, I have to speak. Yes, I'm not online. Yeah, so if we can have the speakers come down. We thought it would be a real gas if we had a panel discussion.